Hello everyone to our seminar. Today, Simon Schmidt is going to tell us about quantum homomorphic strongly regular graphs from the E8 root system.
Yes. Yeah. So thanks so much for inviting me to talk in your seminar. And today I will talk about, as you already said, quantum isomorphic strongly regular graphs from the E8 root system. And yeah, the idea is to start with a graph from the E8 root system and then construct another graph that is actually quantum isomorphic to this. And yeah, please, whenever you have questions, just interrupt me and ask, and then, yeah, let's see. Okay, so there are several words we want to define first. So let us start with isomorphism. So first of all of our graphs will be finite and simple. And we say that two graphs are isomorphic if we find a bijection on the vertex sets such that if I and j were connected in the first graph, then sigma I and sigma j are connected in the second graph. So for example, if we look at the pentagon and the star, and then we take the map that takes the vertex with one color to the other vertex with the other color, then we can see, okay, this is actually an isomorphism between the graphs. Okay, that's nice. And there's actually a funny reformulation of this, or a theorem by Lovász that shows that, okay, now two graphs are isomorphic if and only if the homomorphism counts from all graphs F coincide. Okay, what is a graph homomorphism? Well, it's now not a bijection, but just a map between the vertex sets. And now I just want that if my vertices are connected in the first graph, then they should be connected after applying the map. And now, I mean, by this notation, I mean that the number of homomorphisms from the graph F to G should be the same as the number of homomorphisms from the graph F to H. Okay, but now why are we interested in this? Because yeah, the quantum isomorphism can be characterized in a very similar way, where we now replace the homomorphism counts for all graphs just by homomorphism counts for all planar graphs. Okay, that sounds funny, and now maybe you ask, why is this called quantum isomorphic though? And yeah, the story is a bit from another direction. So it was first a so-called non-local game defined, the isomorphism game. And then for this isomorphism game, we could define perfect strategies using quantum mechanics, hence the name quantum isomorphism. And then later on, it was shown that this is actually equivalent to the homomorphism counts from all planar graphs being the same. Okay, but now what does it mean for two graphs to be quantum isomorphic? Let's, for example, look at different characterizations via homomorphism counts, where we see, okay, two graphs are fractionally isomorphic if the homomorphism counts coincide for all trees, or the graphs are co-spectral, so they have the same spectrum, if the homomorphism counts from all cycles are the same. Okay, now we see, well, trees are planar and cycles are planar. So if my graphs are quantum isomorphic, then they're at least fractionally isomorphic and also cospectral. And if you know the Weisfeiler-Lehmann algorithm, then this, for example, is also shown to be the same as the homomorphism counts for all graphs with tree width k. So one can actually show that if two graphs are quantum isomorphic, then they're indistinguishable by the true Weisfeiler-Lehmann algorithm. Okay, but still, and I think it's always good to know, at Series et al., they showed there are actually quantum isomorphic graphs that are non-isomorphic. So in theory, it could be, okay, my homomorphism counts coincide for all planar graphs, maybe they already coincide for all graphs. but that's actually not the case. Okay, very good. But yeah, maybe so this definition with the homomorphism comes from all planar graphs is nice to show that two graphs are not quantum isomorphic, but maybe it's not so helpful to actually get a quantum isomorphism. And for the other direction, so actually for finding quantum isomorphic graphs, one has to look at so-called quantum permutation matrices. So what is a quantum permutation matrix? So you have a big matrix now with m squared entries, and each entry is by itself an n times n matrix. And it actually fulfills the relations that all entries are projections. So we have uij is equal to uij star equal to uij squared. And if I sum over all rows and over all columns of my big matrix, then the projections sum up to identity. Okay, so why is it called quantum permutation matrix? Well, if you think about the usual permutation matrix and you take the one-by-one matrices, then okay, what fulfills uij equals uij squared for the numbers? Well, it's 0 and 1. And then if I have, or if I look at my usual permutation matrix, then in every row and every column, there's exactly one entry that is 1 and all others are 0. So they sum up to 1, which tells me, okay, so quantum permutation matrices generalize permutation matrices by now considering the entries as larger matrices instead of just zeros and ones. Okay, very good. So what are examples here? So for m equal to 2, it's still maybe not so interesting because if I start with my first entry in some projection, then by my row and column sums being equal to 1, I already know that the other entries in this same row or column have to be 1 minus p, but then this also determines the U22 entry. So this is just one projection. But for the m equal to 4 case, we can see that, okay, for example, this p1 minus p, and the same with q, this fulfills all the relations for any projection, right? Because p plus 1 minus p is always identity. And if I choose any projection p and q, 1 minus p or 1 minus q will also be projections, right? So especially what we see in the m equal to 4 case is that the projections don't have to commute, actually. And yeah, that's where interesting stuff happens. Okay, but now what does this mean for quantum isomorphism? Well, Manchinski and Robinson showed that two graphs are quantum isomorphic, so the homomorphism comes coincide for all planar graphs, if and only if we have such a quantum permutation matrix. But now it has also the relations that the entries, so the matrices uik times ujl are 0 if I is connected to j, but k is not connected to l, or vice versa. So how would you think about it in terms of an isomorphism? Well, if you look at the permutation matrix of an isomorphism, then I also see that, so basically this uik ujl equal to 0 means that I can never map something that is connected to something that is not connected, which is exactly what we want, right? Because we always want to map something connected to something connected. And that's where those relations come from. Okay, but now you see I replaced this n times n matrices by C star algebra elements. And this is just to really get the if and only if. Otherwise, okay, if we just find n times n matrices that fulfill those relations, then we find a quantum isomorphic graph. but there are quantum isomorphic graphs where we can only do it in a more general C-star algebra and not necessarily in the n by n matrices. But gladly, we're interested in constructing quantum isomorphic graphs, and this we do by just considering matrices. So we're good there. Okay, so the title was quantum isomorphic strongly regular graphs. So let's see what we mean by a strongly regular graph. Well, we take a k-regular graph, which just means that every vertex has k neighbors. And then we say that the graph is strongly irregular if we have some lambda and mu, such that adjacent vertices have the same number of common neighbors, in this case, lambda, and non-adjacent vertices, for those, it's the same, but with a different number. And then we say that G is strongly regular with parameters nk, lambda, and mu. If this is fulfilled, and n here is the number of vertices. Okay, and just to quickly check, if we take the 5 cycle, well, it has 5 vertices. Every vertex has 2 neighbors. If I take 2 connected ones, well, there's no triangle, so they have 0 common neighbors. And then it's also not so hard to check that if I take 2 that are not connected, then I can find a common neighbor for all of them. So then we say that the 5 cycle has parameters 5, 2, 0, 1. Okay, very good. So let's come to our first strongly regular graph. And this comes from the E8 root system, which consists of 240 vectors in R8. And here by EI, I just mean the unit vectors with 1 in the ith entry and 0 otherwise. And then, we take those. So the plus minus EI plus minus EJ is just, okay, you have 2 non-zero entries in your vector that are either plus or minus 1. And then X is just, a 1/2. And then I just want that they multiply. Okay, I think without the 1/2, they should multiply to 1. So it's just an even number of minus 1s. Yes. And then our graph will be the orthogonality graph of the 120 lines spanned by the E8 root system. What do we mean here? Well, our lines will just be lines through the origin, so lambda times the vectors we have here. But above there are, so for plus x, there's always minus x. So we just, x and minus x will be in one line. So we just get 120 lines instead of 40. Okay. And what do we know about this graph? Well, this graph is strongly irregular with parameters 120, 63, 30, and 36. And later on, it will be nice to know that it actually has independence number 8. Okay. And now what we want to do is we want to construct a quantum permutation matrix such that later on we can find a quantum isomorphic graph that we can get from this quantum permutation matrix. And how do we do that? Well, we first define matrices as above. So just, okay, I's identity, X is something like Pauli X, that is Pauli Z, and then Y is just X times Z. And then we can actually see that if we take the tensor products of such matrices, then the maps that send X to M times X are actually automorphisms of the graph. Okay, how do we see that? Well, one can check that all matrices X, Z, and Y are actually unitaries. And then, so in the inner product, if we have XY orthogonal, then also MX, MY are orthogonal. And so the the thing that is harder to show is that, okay, if I apply M to X, then it's actually also again in the vertex set. But this one can just check by writing it out and seeing that, okay, the matrices we get are just signed permutation matrices that send in or that change an even number of -1s. And then we see that we're again in the set of vectors that we had before. Okay. And then using this subgroup, so yeah, this will actually give us a subgroup that is isomorphic to Z2 to the 6. And then what we see is that the action of this subgroup on the vertex set has 15 orbits, and we get a partition into 15 cliques of size 8 of the graph. And yeah, just to give an idea what they look like, it's pairs of those vectors with just 2 non-zero entries. Those are forming 7 cliques, and the other 8 cliques are the ones from the vectors that just have ±1s. And this notation x12 just means that it's the vector where all entries are 1, but in 1 and 2 they have -1s. Okay.
Sorry, can I just quickly ask?
Yes.
How is this isomorphic to Z2 to the 6? Because I thought that Paulis do not commute, so this would not be an abelian group, right?
Yes. Yeah, it's sort of the funny thing is that, okay, we have lines, and then 1 and -1 are the same. So somehow x and minus x, so yeah, xz and minus xz will be the same, and then we get the abelian group. So it's not immediate, but yeah, since we're working on the lines, it's fine. Thanks. Okay. And now how do we get a quantum permutation matrix from this? Well, let us now, so for each vector or even line x, we can take the rank 1 projection and then define a quantum permutation matrix by doing the following. So just as a reminder, so we have now those 15, we have this partition into 15 cliques of size 8. And what we now do is we pick one line from each of those sets, so those WIs, and then we define UXYI to be the projection onto this line, and then I multiply by MXY, which is the matrix that sends the line X to the line Y. Why does this exist? Well, it exists because, so this is in the orbit of the subgroup, and it's actually unique up to stabilizers. Okay, but yeah, since we can pick any of those lines WI, the matrix is not unique at first. So this is, this depends on the WIs. Okay, and then what one can check is that, so for each I, we get a block that looks like this. So we have a block of 8 different projections. So yeah, remember that, so MXY is a unitary, so the U's will be projections. And then what one can show is that if we fix X and let Y go through all VI, then actually all rank 1 projections associated to this part of the partition will show up. And now remember that the partition gives us cliques of size 8, and we are looking at the orthogonality graph. So so all those cliques give us basis of R8. And now if we look at projections that are associated to basis of R8, then those actually sum up to identity. And yeah, this matrix down here just tells you, yeah, the structure, which is not so important for now. It just says that, okay, in every row and every column, we have projections associated to basis of R8. So the row sums and column sums will actually be 1. And we can put it into a very big quantum permutation matrix for every VI putting it on the diagonal. And this is actually the quantum permutation matrix we will work with now. Okay, very good. So what do we do with this? We need a nice lemma. And yeah, remember we still use the same partition as before into those VIs. And now we take, yeah, two elements or two vertices from VI and 2 from VJ. And then what one can show is that if both of them are connected, or if K is connected to L and S is connected to T, then we actually have that the entries of the quantum permutation matrix are 0 if and only if the lines we chose before are orthogonal. And similarly, similarly, if one of them is connected, the other one is not connected, then we get that the product is 0 if and only if the lines are not orthogonal. And maybe just to get a rough idea, so this product will then, so the proof of this boils down to finding the right M such that the M's cancel, and then we just have PWI times PWJ written in between the M's, which then means, okay, they are, so the product of the projections is 0 if and only if my lines are actually orthogonal. Okay, but how does this help, right? So let us have a look again what we actually wanted to do. So recall that 2 graphs are quantum isomorphic if we have a quantum permutation matrix such that I have this product, and if vertices are connected in the first graph, they shouldn't be connected in the second graph. So exactly when the product is 0. Okay, and now if you look at our lemma, we see that we almost have this somehow. Because so far for the part 2, where K is connected to L and S is not connected to T, we are already good, right? But part A is somehow not what we want, because here both are connected, but that doesn't really help us for the quantum isomorphism. Okay, so we now define a new graph depending on our choice of W's. And we take the vertex set to be the same as of our original graph. But now what we do is, so we take also the same vertex partition. And then if we have a vertex in Vi and the vertex in Vj, such that the W's are not orthogonal, then we are happy with our connections. So then S and T will be connected if and only if they already were connected. But now if we take S in Vi and T in Vj, where now the picked lines are orthogonal, then we say, well, now we want the vertices to be connected if and only if they weren't connected before. Okay, so how does this help? Well, what we can actually show now is that so the graph GEH and the graph GW are quantum isomorphic, non-isomorphic, strongly regular graphs. Okay, but how do we do that? Well, so the quantum permutation matrix we constructed actually fulfills exactly what we wanted to do. And how does this work? Well, as I said, so if we look at the lemma, then our second case is already good. But now if we take our first case and say that Wi and Wj, so they're actually orthogonal, then our connection will also change between the S and T's. So we will actually get exactly what we want. So we will actually end up with the product of Ik and Ujl being 0 if I is connected in GE8 and K to J, and K is not connected to L in GW. Okay, that's nice. So we constructed this quantum permutation matrix that actually fulfills what we want. But now we still have to show that the graphs are not isomorphic, right? Because in principle, okay, we can have a very nice quantum permutation matrix, but it could be that the graphs are still isomorphic. But now if you look at our set W1 to W15, that one can actually see that this is an independent set of size 15 in GW. Okay, how does this work? Well, so if the graphs, if the vertices, so let's say we take Wi and Wj that are orthogonal, then the graphs, then the vertices were connected in GE8, but now by our definition, we see that they're not connected anymore, since we have that it changes if Wi and Wj are orthogonal. So they are non-adjacent. Okay, but in the case of Wi and Wj being non-orthogonal, then they were already not connected in GE8, but we don't change adjacencies, so they're still not connected. So this means that none of the Wi, Wj are connected in GW. So we get an independent set of size 15 in GW. But we knew that the independence number of GE8 was just 8. So that's good, right? Because then this already tells us that they cannot be isomorphic. Okay, very nice. But another question we might have is, okay, but you had all those choices for different W's. Is GE8 quantum isomorphic to a lot of graphs? Well, maybe, but at least what we know is that if we take different choices of W, then actually the graphs will be isomorphic. So the only thing we got was there's essentially one graph that is quantum isomorphic to GE8, which is still nice. Okay, but then one might wonder, okay, now we have this GW. Did this appear anywhere else, maybe before? And the answer is actually yes, which is quite nice. So, okay, how do we describe this other graph then? Well, let's say we take this affine polar graph with a vertex set f2 to the 6, and then we have a quadratic form such that the vertices are adjacent if quadratic form on this x plus y is equal to 0, where the quadratic form is defined as multiplying the first and the second and the third and fourth and fifth and sixth entry of the vector. And then a graph that was already defined before is the following one, where one takes as vertex sets. So one can check that the graph above actually has 240 orbits, cliques of size 8, and there's an action of z2 to the 6 times a8, and this divides it into 120, so 2 times 120 cliques, and then one can take those as vertex sets and say that those vertices are adjacent if the associated cliques have 2 vertices in common. And then the funny thing that one can show is actually that the complement of the graph I just described briefly is actually isomorphic to GW. And maybe just to give you the idea how to connect those graphs. So another way of thinking about this affine polar graph is by, instead of taking f2 to the 6, you can take once again those tensor products of Pauli matrices, but now in the exponents you put those z1s up to, so let's say you z1, z3, and z5 correspond to Pauli X, and z2, z4, z6 correspond to Pauli Z, and then one can actually find a similar description using free tensor Pauli matrices for the graph. And then similar, since we also saw that, so we had this action of the Pauli matrices on the GE8 graph, one can define one can give a similar description in terms of free tensor Pauli matrices for its GW. And then, funnily, one can use this to actually show that the complement of the graph above and GW are actually isomorphic. Right. So, okay, we have this pair of quantum isomorphic graphs. So what are the properties that might be interesting? Well, only one of them is actually distance transitive. So GE8 is distance transitive, but G1 and then also its complement is actually not. So if we look at the orbits, one can actually, one has 4 orbits in the G1 case. And one can also see this in the size of the automorphism group, which is definitely larger in the size of, in the case of GE8. And another thing that we already saw, that the independence number of the complement of G1 is 15, or at least we saw an independent set of size 15, but independence number of GE8 is just 8, which yeah, I think a nice comment for the experts actually shows that GE8 has quantum independence number 15, but just independence number 8, which is quite nice, I think. Okay, so now we have the properties of this graph. So maybe we can think about, can we find more pairs of quantum isomorphic strongly regular graphs? And yes, we can actually do that. And we'll do this by using Godsil-McKay switching. So how does this work? So we take a graph G and a partition of the vertex set where we have some distinguished set D and also C1 up to CK. And now we want that any two vertices in CI have the same number of neighbors in CJ. And then a vertex in D has either 0 Ni or half of Ni neighbors in CI, where Ni is the size of CI. And now we define a graph, switching graph to this, where for each V in our distinguished set, we just delete the Ni half neighbors in CI, and then join instead the others. And so that's a way of constructing co-spectral graphs, which, okay, if we have a strongly regular graph and do the switching, then we end up again with a strongly regular graph. Okay, so how can we use this? Well, so what we can show is that if we have a quantum isomorphism between two graphs, or if we have two quantum isomorphic graphs with a quantum permutation matrix U, and this is of this special block form, so we once again have this big vertex partition. And now we take a partition of the, so we define our partition as in the switching case, but now this partition just collects, so it's a disjoint union of the VIs we have in our quantum permutation matrix. And then what one can show is that, okay, if all properties for Godsil-McKay switching are fulfilled with respect to such a specific partition, then actually, if I switch both graphs, then they remain quantum isomorphic. Okay. So what does this mean? Well, in our case, what we saw was that, so what we did, we took our graph on 120 vertices. We defined a quantum permutation matrix that actually consisted of those 15 blocks of size 8. And then what is left to show is that the two graphs we have defined, they actually still fulfill the properties for Godsil-McKay switching with respect to the same partition. Remember, we used the same vertex set, so we also partitioned them in the same way. And then we use the switching on both, then they actually stay quantum isomorphic. And this is actually true in our case. And so if we take different, so in our vertex partition, if we take different sets, then the vertices in there have exactly 4 neighbors and 4 non-neighbors in the other set. So we can actually do that. And one can also show that we can find more quantum isomorphic strongly regular graphs in this way. And another way to find more strongly regular graphs, which is not preserving strongly irregularity, is actually deleting some of the partitions, some of the cliques in the graphs. Because the funny thing is that since we have such a big discrepancy between the independence numbers, we can delete some cliques and still just go down or up in the independence numbers by 1, which means that we can delete more than one clique, for example, and still show that the graphs are quantum isomorphic with the same quantum permutation matrix, but non-isomorphic since the independence numbers are still not the same. Okay, very good. Then let me sum up what we did today. So we constructed 2 non-isomorphic, but quantum isomorphic strongly regular graphs. So, which means, okay, they actually have the same homomorphism counts from all planar graphs. And the quantum permutation matrix we used was from a subgroup of the automorphism group, which could be obtained by a tensor product of Pauli matrices. And then having this pair, we saw that if we use Godsil-McKay switching, we still end up with more strongly regular graphs that are actually quantum isomorphic but non-isomorphic. And that's already everything I wanted to say. So thanks for your attention.
Thank you so much. Are there any questions? Oh, questions for Simon.
I have a question about the choice. You make some choices maybe in first choosing some subgroup related to the Paulis, and then later you choose these representatives W. And I think you showed that the graph GW doesn't depend on W, right?
Yes, yes.
But okay, so I was wondering, can you maybe like embed these Paulis in a different way to get another quantum isomorphic graph, or do you know something in
how would you do that? I mean, it's a good question, but I don't know at the moment.
But I guess maybe what I'm asking is, in general, you don't know whether or not this graph that you started with is quantum isomorphic to more strongly regular graphs than just this one that you constructed.
Yes, that's correct. Yes.
Yeah, and I guess in general it's hard to decide quantum isomorphism.
Yeah, that's also true.
Okay, thank you.
Yeah, but maybe just to give another comment to that. So there's this. So for subgroups, there's this more general theory by Musto, Reuter, and Verden, which showed that you get quantum isomorphic graphs by looking at, I think it was called central type subgroups of with coisotropic stabilizers. The problem is that it's very hard to come up with those. So it's nice to know that this is what you need, but somehow you still have to be lucky that your subgroup actually fulfills this.
And the one in your example fulfills it?
Yes, but at least for me, it's easier to calculate things directly instead of trying to do it very abstractly and then, yeah, at least before knowing if it works or not.
Yeah, okay. Well, thank you.
Yeah, are there any other questions?
You might have mentioned this and I might have missed that. Do these graphs have quantum symmetries?
Yes, so at least the GE8 has quantum symmetry. No, sorry, the complement of G1 has quantum symmetry, since by a more general result, so one can show that two graphs are, or if two graphs are quantum isomorphic, then the quantum automorphism group of both graphs, they have to be monoidally equivalent. And now since the automorphism group of G8 is bigger than the automorphism group of G1, this actually means that the quantum automorphism group has to be at least, or has to have at least size, the size of the automorphism group of GE8. So it cannot be equal to the automorphism group. So it could be that the quantum automorphism group is still finite dimensional, but at least it has to be bigger for G1.
So does it mean that it's possible that there are two quantum permutation matrices that relate the same pair of graphs?
Can you say it again?
Is it possible to have two different quantum permutation matrices that, or this pair of graph that establish the quantum isomorphism?
Yeah, that's very well. I mean, that should be true, yes, because usually, if you have quantum symmetry, then you can compose your quantum isomorphism with a quantum automorphism. Yeah.
I'm curious if there's any that is not in the block diagonal form. Yeah.
Yes. I mean, there should be some funny tricks one can do just by using some isomorphisms. I think one can fill up the whole thing, but it's not very helpful, let's say. Or it will look the same, but I just it will not very much be different. It will just be using isomorphisms to fill up everything, but I don't think it's very different from what we have now. But maybe there's something more different, but I don't know.
Thank you.
Thanks.
Simon, I need an explanation. You said if there was a quantum permutation taking one graph to another, that the automorphism groups were monoidally equivalent. What does that actually mean? Monoidally equivalent.
Yeah, so this is for quantum automorphism groups, and then we look at irreducible representations of this quantum automorphism group, and so there's an isomorphism between those irreducible representations, which might not be very helpful. So for me, it's not necessarily enlightening, but it gives you or sometimes it gives you an idea whether or not a graph has quantum symmetry.
Okay. And how does that occur? I don't see that at all.
Yeah, it's not trivial to show that.
Okay. Thanks.
Thank you.
May I ask a question?
Yeah, I think we're going at the same time. Okay.
Oh, sorry.
You go first.
Oh, okay, thanks. Yeah, I was just wondering, so do you know for this G of E8 whether the quantum automorphism group is finite dimensional or not?
I think I know basically nothing about it, but it's a good question. Yeah, I mean, it's distance transitive, so I should try to work a bit on it, but I don't know at the moment.
It's connected to my question that I wanted to ask, do you know if either of these graphs satisfy what is now known as Schmidt's criterion? So your criterion, having two disjoint automorphisms.
Uh-huh. I think I should have tried this at some point.
And
So I
you
would
think
say,
there's so many automorphisms, maybe they just
right.
said, and once you have that, then you immediately get that the quantum automorphism group is infinite
Yeah,
dimensional.
that's true. Yes, I would just think that if it's true, then I would know because I would have tried it at some point, but I don't know at the moment. So maybe I just didn't do the calculation.
Actually, I think getting disjoint automorphisms might be fairly difficult, even though the group's large.
Right.
It tends to force imprimitivity on the graph. And so, but I mean, yeah, I don't know whether there are disjoint automorphisms or not. I'm just giving you a guess, but I'm not. It could go either way.
Yeah, my guess would also be that there are no disjoint automorphisms.
Yeah. That's
Any more questions?
actually a comment on the disjoint automorphisms. If you've got it, if two automorphisms, if their intersection is a port size 1, then they compensate as a 3 cycle. And so the automorphism group is basically the outline group. And so you can start pushing the supports of this automorphism around, okay? And either you end up either with a block system, in which case you're primitive, or you're getting them overlapping in something smaller. And so it's, I think for a primitive automorphism group, it's going to be a little unusual to have elements with disjoint support.
Mm-hmm.
But yeah, still, that's an open question.